parts by this institute, thanks to the microphysics. This is called second station of the Alice beyond spectrometer. And this is the largest cathode pad chamber ever built. This is the longest wire. This is a wire chamber, long wires put together, and that gives you very high position resolution. A total 200,000 cells. And then of course there is something with the new term comes called Manas. This I'll explain a little bit more, because this is something which we are all proud of, and this is something which is again the evolution, the result of evolution. What is Manas? Manas is essentially a ASIC or a chip, which is application specific, which can serve 16 channel. It can do amplification of the signal, which is coming out of the gaseous detector, which does the shaping. All those who might have done a little bit electronics, electronics know, you have to have the shaping. Then you track and hold, because unless when another collision comes, that charge should not fall on your earlier one. So, and this whole thing comes as Manas. And this is within India. And this is where there is a collaboration. So there is a photograph taken when this Manas, when there are 4 boards of Manas put together, and this is how it goes to one detector. Now, interestingly, this Manas, earlier we used something called Gasiplex in star, where the chip was from CERN, but here the ASIC, which is multiplex, that means 16 channel put together and read it out. This is also ours. It was built in Semiconductor Complex Limited in Chandigarh, and this served not only PMD, this served the muon spectrometer and some other detectors. And then now comes another effort, because this is again large data volume. If you now put together your Alice data in a CD, whatever volume you have, 1 GB, 2 GB or whatever, and stack them together, if you have 1 year data, this is what the height of the stack will be. Here the aeroplane flies. So now if you analyze these CDs and try to understand your quark-gluon plasma, try to understand your Higgs boson, not only you, maybe several generations after you will essentially tell you that whether quark-gluon plasma is found or not, or whether the Higgs are found. But then CERN discovered or declared the results within few months. How did they do it? This is something called grid computing. So all the computers in the collaboration, they were all active, and they were essentially connected to high-speed internet. So whichever you give a job, whichever is free, the jobs goes there, gets executed and come back. So essentially you have all computing power put together. It is not by one, and that's how it is. We have a grid computing in next door, that is in BECC, which have already served 16 million jobs, and this is running 24/7 with more than 90% efficiency. Now I'll just quickly go through some of the results, because these are the PMDs of 4 generations that I have talked about. So one, of course, you measure the number of photons and the distribution of that, or you measure their pseudo rapidity and then measure the distribution. This essentially tells how many photons are produced in particular pseudo rapidity region. This is from W93. This is similar results from W98. Again, number of photons, as it goes from 200 to 500, the number of photons goes high, and it depends on the number of participants linearly. And this is what is the DCC search, because our motivation was to see if there is a DCC formation, there is that chiral restoration or not. So this is what is Belam's thesis, part of Belam's thesis. So this is what is the confidence limit. So this region is excluded. That if you don't have a DCC which is having all the event of 80% or 100%, and then you have 10 to the power 5, with 1 in 10 to the power 5 events there is a DCC. This you exclude. It must be lower than that, and similarly for the lower size DCC. And this is what is the correlation between number of charged particles and number of photons. And this is what is one typical event where there are charged particles and photons put together, and you just detect them. Similarly, we have done for star, which is published in Physical Simulator. Again, the measurement of the number of photons and number of charged particles. Again, we saw there is a very interesting phenomenon that if you take the pseudo rapidity distribution and if you subtract the rapidity of the beam, all the particles, whatever the energy it is, at different energies they fall one over the other. As if there is no particles which will be produced with rapidity higher than this. This is what is called limiting fragmentation. This is an important phenomenon which was essentially discovered and established by us. Now again, our main goal to find if there is a fluctuation. This is the thesis. And so this is charge and photons, event by event, and this is what is the distribution. If there is a tail anywhere, that means there is a fluctuation. There is a measure called moments of different orders, and as you can see, this is what is from model like ETR and hygiene, which is essentially gives to 1, and this is what is another model which gives in different direction. This is the data. So there is some difference between the model and the data that essentially tells you that something is happening. And this is what is the measurement in Alice, which is for at PP and other data analysis ongoing. Now at this point of time, I want to take a little bit of break and then come back to phase diagram again. You might have remembered that phase diagram. It was only white and colorful, nothing else was there. And today, if you ask any theoretician, because this is basically a photograph, this is a picture drawn by some theoretician. There is no scale maybe sometimes. So you see how crowded it was? It is not crowded in this zone, in high temperature zone. In high temperature zone, only difference is that there is one point which has been added. That is called, that means you have already reached in weak and LHC to the quark-gluon plasma phase, and this is what is the error on your temperature, which is 156 MeV plus minus. But then there is nothing more which is interesting there. Of course, if you go down there, then this is the crossover transition. There will be a change from first to second order. And then most interesting part is here, which is essentially a high density. High density, there are many other phases which is happening. Not only just quark and gluon, there is a quark-ionic phase, there is a neutron star phase, there is a color superconducting phase, and all these, if you want to explore, you don't go to very high energy like weak and LHC. You go to relatively lower energy, which will be accessed by these accelerators, which is FAIR and others. So I will just show you where we are in this direction. So this was in 2007 in Delhi. There was a meeting of European Union in Delhi, and that time one agreement was signed. This was our then foreign minister, and many of you kind of can recognize here. And this was the then science and technology minister and German science and technology minister and secretary, and others. Now that essentially that agreement says India will be a partner country of building this accelerator, which is called FAIR, which is called Facility for Antiproton Analysis. And the sign that the formation of the FAIR happened in 2010, that was in 2007, this is 4th October 2011, which formally it was signed. These are the founder countries which signed, and this is Dr. Ramaswamy on behalf of India, he signed as a partner country. And this is what, if any of you go to GSI now, you will see some the flags of the partner countries at the central place. Now what is FAIR? GSI, this is the existing GSI, this is some German name of heavy arm facility, and that facility is credited in discovering seven periodic table elements. One of them is Darmstadtium, from the name of Darmstadt. Another is Hessium, which from the name of Hessen, the state where Darmstadt is situated. So these exist already. This has been running for several decades, and this is the one which is being built. So that means beam will come from here. This is also existing, and then it will go to a ring which is called synchrotron, and initially it will be 100 Tesla meter rigidity, later on it will be 300 meter, and then it will be, you will see different, it will serve different experiments. Because FAIR is something which is not only for particle physics, but the physics reach of FAIR essentially starts from 10 to the power minus 6 seconds, where you know quark-gluon plasma, to today, which is essentially knowing the outer space. So we are interested here. We have already talked about high energy or high temperature quark-gluon plasma, and here the energy is not high. In FAIR, energy is only 45 AGV maximum, 35 AGV maximum. What is more important is the intensity, which is 10,000 times higher than anywhere else, or 100 times for the antiproton beams. So it is a high intensity experiment, and it is something where the energy is not high to pass through each other, but it will stop, and it will create something like a system of core of neutron star. And this is what we are interested to study. 5 minutes, yes, sir. So these are the physics program that will essentially cover, including the one which I want to draw attention here. You can see Higgs boson. Higgs mechanism explains the mass of the elementary particles. Now if you look this color, this green one, this essentially shows the fraction, if you talk about the total fraction of mass which is explained by Higgs mechanism. So for charm, for bottom, for top, it is fully explained. That means Higgs mechanism can explain everything. But for up and down, which is the light flavor of which all of us are made of, there only 5% are explained by Higgs mechanism. The rest 95% are to be explained by chiral symmetry, that means the interaction of gluons, and that can only be understood if you formulate a medium which is like an neutron-star medium. And this is what one of the most important studies that we will do with an experiment again. And this is a fixed target experiment, unlike STAR and ALICE. And there are many detectors built by different countries. This is the detector which we are building. Again, this is a muon spectrometer with the tradition that we have. And this muon spectrometer will handle up to 10 megahertz collisions. This is unprecedented. No, LIC handles something like hertz, maybe kilohertz in ALICE. Maybe these are the other experiments. STAR is having kilohertz, ALICE is having 10 kilohertz, and this is where our experiment will look like. And if you now take your camera, photograph in 10 million photographs per second, you can imagine how speed it will be. So this is a completely new type of electronics, new type of detector that we need to build, and that is what we are doing. This is something called gas electron multiplier. It's a gaseous detector, but there is no wear. There are foils which are 50 micron thick with 5 micron on top and bottom. Particle goes through it, and there is a huge electric field in the holes, and it gets multiplied, and you get the signal. And this is what is typical one detector that we have built. This is in our lab, large size gem foil that is being put together. And we tested these detectors in a setup where there was a magnet and there are other detectors in the setup. But then, as you know, in 2020 June, that was the pandemic time, but the GSI was on. So we controlled our detector. Fortunately, the detectors were all installed before that. So we controlled our detectors remotely, and this is one of the midnight shifts that where you can see our colleagues, they are taking data from here. But then this year again, we could go there to GSI, put these experiments again. This is our detectors, this is the beam pipe, and this is where particles are detected. This is the beam spot that we could detect, and this is the particle, this is the off and on steel. So where there is a beam, then there is a nice time correlation. So this essentially shows that all the detectors are working the way it should be. We are now ready. Mechanically, this is how it will look like. This is what is our detector. If you can look at that, this is 120 ton total, and this mechanics is supposed to come from Russia, which is having now some problems because of the international scenario. Now, where is FAIR now? So far as the accelerator is concerned, in 2007 there are some among the audience who are there in this photograph. They participated on July 4th on 2017 in groundbreaking ceremony, and this is how it looks like from top at that point of time, and this is how it looks like today. The main ring, which is essentially a 60-meter deep, 60-meter wide and 20-meter deep, this is already built. And this is the GSI, which you can see and then we talked about. So beam will go from here, circulate and get, and then experiments will happen somewhere here. This is north area, this is south area. This is the close view of the ring. And if you go below the ring, this is how it looks like. So the ring is essentially ready, and it is ready for the accelerator items to be installed. And this is some of the accelerator items. This is power converter, which is built in ECIL Hyderabad. 235 of them. This is the picture taken in GSI where it is in their warehouse and stayed there. There will be some 400 more which are to go. And these are the ultra high vacuum chambers, which is built in a company in Bangalore called Vacuum Technique. And this is what is the shipping, and we all participated in the shipping. And this is how, when FAIR will be ready, this is how it will look like. So you will not see anything from top. You will have to give back your all the greens, and experiments will happen. Now I would like to conclude by again the phase diagram. So we started the phase diagram in 1991. We went with WA93. Then we went to WA98, which is again scintillator detector, so it's 55,000 cells. And you can see the change in the phases and maybe modes. And this is what is the detector in STAR, in relativistic heavy ion collider Brookhaven. which is having 80,000 cells, gaseous medium. This is in Alice, which is having 200,000 cells. And then finally, this is what is fair, which will essentially cover this region, not very high energy region, and this is how it looks like. So it was initiated by one person, and that I don't need to tell again. And so as Dr. Sinha is looking very carefully in the agreement, I am sure he will also look carefully whether when this facility will be over. And this is the cave which is already ready. And we are supposed to install the detectors in 2023. There are of course ups and downs and the problems which you are all facing like any mega science project. But then this is the journey that we have. We started with 7,600 cells with W93 photon multiplier detector in 1991. This is my thesis experiment. We have gone a long way to 55,000 W98, 80,000 gas proportional chamber in star at Lake, 200,000 gas proportional cells in Alice. And then now we have built the largest beyond chamber in Alice, which is still making data. And the entire beyond chamber in CBM, which is at the heart, is being built here. Thank you very much.
Thank you very much, Ashish, for a very, very interesting talk. And that was a very interesting account of the advanced detector developments for high energy nuclear physics. And as Shubhashish has shown in his slide, Professor Vikas Sinha has been behind all this development, his initiatives and inspirations. And the FAIR project, which will be completed, let's say, in another 4 or 5 years' time, that will provide our younger colleagues an excellent opportunity to do the frontline experiments on equal basis as the other international community, because we are participating, as Shubhashish told, in the construction of that machine and the development of detectors. And we should all thank Professor Vikas Sinha for taking these initiatives. So now the talk is open for discussion.
Thank you for this detailed drawing of the historical tool. So you discussed many times about the phase diagrams. So I was thinking that when you go from LEAK or LHC to FAIR-like projects, you said that the density is higher than the 10%. So how do you achieve that?
How do you achieve it?
The nucleus, you do different types of nucleus?
No, energy. That's the only thing which is energy. If you have very high energy, like two nuclei, they are colliding. You look into the center of mass field. They are colliding and they will essentially energy is so high that essentially pass through each other. And the baryons, which is in their nucleus, that means you have 197 core, you have 208 in lead, they pass through each other. And the baryons are gone. So in the middle you have essentially the field, which will create the particles, and that particles, quarks and gluons and all others. So in the medium it's a baryon free, it's like RD universe. There is no barrier. So this is what is LEAK and LHC. Now you think of a situation, the energy is not that great. That means it doesn't pass through each other. It's not transparent. It just stops each other.
So enough to break the nucleus and have
yes, so inside one nucleus, essentially you enter, let's say 3-4 nucleus in the same volume. So your density essentially becomes 3 to 4 times higher. So that is how you achieve this. This has been shown that you essentially, if you take just, it's a very simple calculation you do. You take something like the nucleus and calculate the radius, let's say gold nucleus. You calculate the total volume that it has and how many 208 or 197 you have, and divide how much free volume, how much free space you have. Now you take a 2 or 3 times more density inside this. So all the free volumes will essentially be filled. So at that point of time, one proton, the quarks of one proton will not know where from they have come. So they will all get mixed together and you will essentially get a soup of quarks and protons. That's what happens in neutron star, core of neutron star.
I have one more question regarding what you said about the fish shower involved with W93. So how it exactly helps, like your calorimeter or your detector is not that much fine granular that
No,
it
it's
will-
not. It's not a problem of granularity. The way you detect photons is by electromagnetic sound.
Right.
There is absolutely no other option, but that is what you have to do. Now, when you detect in, let's say, barrel region, where you put a calorimeter, then the density of photons is low enough so that one shower doesn't fall over the other,
Right.
because there is a distance between them. Now, in the forward region, as these are forward focused, density, that the number of photons per centimeter square is much higher.
Right.
Even though rapidity is essentially big, but spatial density is high. That time one shower will fall over the other. Now if you now put a thicker detector, not pre-shower, so let's say it is a 3 radiation length, instead of that you put 10 radiation length. Then 2 or 3 photons will essentially give you one shower, and you cannot detect whether it is a 3 photon of higher energy or it's a 1 photon of higher energy. It's like that. So that is the only way that you have to put it as a pre-shower so that you can separate them, but at a cost that you do not know the energy. This is always our handicap. With our PMD, we cannot do much except measuring the number of photons. If we would have known the momentum of the photons or the energy of the photons, we would have done much more physics, even with the DCC service. Because this is always a kind of a problem with us. But that's how it is. In forward region, you can't put a calculator. Thank you.
Sir, thank you for the presentation. It is very nice to know the international projects like AFAIR has a very big, larger facility, means it is a very larger project. So this project where it is situated, and second is whether it is a future accelerator, large accelerator project, and with that ALICE and LHC, which is LHC is 27 kilometer underground tunnel. It is also exist, and also the experiment will be going on in it.
That's a very good question, of course. First thing is that let me tell you clearly that FAIR is not the largest. LIC is the largest. So even if you talk about cost, even if you talk about size, even if you talk about total space it takes, LIC is the largest. Okay. But FAIR is the largest upcoming facility. That means LIC is already done and it's taking data. FAIR is the one which is having total cost of about 4 billion euro. So you can imagine how it is. Now, when you asked about the comparison between LHC and FAIR, LHC is a very high energy machine. That means the particle beams will be like if you take out a number, 5,500 GeV. But here we are talking about 50 GeV. So the kind of physics that LHC will look after, like I was discussing, the relationship pass through each other, it is a very high one. So it will create something like early universe, where there was only energy and nothing else. But here, as the energy is not high enough, it will stop, and it will create something like the core of neutron star. So it's a complementary physics that we will look at, comparison to LHC, and FAIR is another one. FAIR will have a nuclear physics facility. It will do completely new nuclear physics facility. It will have an atomic physics facility. It will have a plasma physics facility. So FAIR in that sense is a multi kind of physics facility that will come. And India is a partner country of that, third largest contributor. And in fact, now it is second largest. If you talk about...
Okay, thank you, sir.
It will provide very intense beams.
Yeah, it will be, intensity is higher than...
Physics, with very low cross sections. So more questions, comments? Well, if not, let's thank Dr. Shubhashish.